Hello and welcome to lecture 43. In last lecture, we were solving the cycle analysis for two spool mixed flow turbofan engine configuration, and as we have discussed, this data which is available for this numerical, it is for low bypass ratio engine which has number of fans which is generating the pressure ratio of 3.85, compressor pressure ratio is 8, and we have the information available in terms of isentropic efficiencies. From that we have done our initial cycle analysis, where we have done our calculation for the net thrust generated by this engine at say ground condition. We have calculated our thrust specific fuel consumption, propulsive efficiency, thermal efficiency and overall efficiency. Now, let us move next step. We are more interested in terms of what will be the effect of different cycle parameters on the performance. When we say performance, they are mainly thrust or say specific thrust specific fuel consumption, fuel air ratio, propulsive efficiency, thermal efficiency, overall efficiency, and this kind of configuration. Here we are having the effect of overall pressure ratio, in sense we can have the variation of fan pressure ratio, we can have variation of say compressor pressure ratio or HPC pressure ratio. We can check with the bypass ratio in order to optimize this bypass ratio. We can study with say variation of turbine entry temperature on the performance, different component efficiencies. Here at this moment we are discussing about the ground condition. So, let us look at what all are the effects of this parameter. So, very first parameter we will select, let us say fan pressure ratio. So, putting other parameters to be same, suppose I say my bypass ratio, say my compressor pressure ratio, turbine entry temperature, that is what we are putting to be constant. If that is the case, let us see if we are varying our fan pressure ratio, say somewhere here we are having say our design pressure ratio. It says with increase of fan pressure ratio, our thrust, that is what will be reducing. On the other side, if you look at here, say when we are having our fan pressure ratio to be on say lower side, our thrust, that is what is increasing in slight number. The reason it is clear, you can say this fan that will be rotated by our LP turbine. So, when we say we are increasing our fan pressure ratio, basically work required to rotate that fan will be higher, and that is what will lead to reduce the exit temperature from the LP turbine, okay, and that is what will be affecting on our exit velocity, and that is the reason why we are having say reduction in thrust, but that number is smaller, we can say. Next parameter we have is a thrust, say specific thrust. Here in this case similar trend we are getting as the thrust, because it is in terms of thrust divided by say my entry mass flow rate or say air mass flow rate, and that is what is constant. That is the reason its specific thrust with increase of fan pressure ratio, that is what will be reducing. Now, let us look at what is happening with our thrust specific fuel consumption. So, here in this case it says when we are increasing our fan pressure ratio, for this particular case with the increase of thrust, we will be having reduction of thrust specific fuel consumption, okay, and this is representing our thermal efficiency. So, when we are increasing our fan pressure ratio, the thermal efficiency that will be improved by few numbers. So, this is representing our design condition, okay. So, let us look at what is happening with the next parameter. Let us consider say parameter to be say compressor pressure ratio, putting fan pressure ratio, turbine entry temperature, bypass ratio to be constant. Here in this case, if we look at when we are increasing the compressor pressure ratio, we will be having say reduction in the thrust, and this reduction in thrust, that is because of reduction in our exit velocity. Okay. At the same time, that is what has been correlated in terms of my fuel air ratio or fuel consumption. Since my thrust is reducing, we will be having reduction in say specific thrust, But at the same time, if we look at in terms of my thrust specific fuel consumption, with increase of our compressor pressure ratio, the specific thrust, that is what will be reducing with. So, it is giving the indication when we are looking for say special kind of configuration. Be careful here, in this case we have kept other parameters to be constant. Suppose if I will be plotting this with say increased of turbine entry temperature, then my thrust will be on the higher side, because of my say turbine entry temperature is higher. Same way here, my thrust specific fuel consumption also will be increasing with the increase of turbine entry temperature. So, just careful in terms of understanding, these are with the fixed numbers what we are discussing at this moment. And just look at what is happening with the efficiency. In this efficiency term also, with the increase of pressure ratio, we will be having the increase of thermal efficiency. So, that is what is the attraction in terms of say achieving the higher thermal efficiency, and in order to achieve say lower thrust specific fuel consumption. At the same time, the specific thrust also is on the lower side. Okay. Now, let us look at with what is happening with the bypass ratio. Say when we are increasing our bypass ratio, we can say under that configuration we will be having the reduction of our exit velocity, because since my bypass ratio is increasing, accordingly my core mass flow rate what is going inside the engine, that is what will be on the lower side. That is what will lead to reduce the thrust. The same trend we will be getting in terms of specific thrust, and if we look at in terms of my thrust specific fuel consumption, that number also is reducing with the increase of bypass ratio. But as we have discussed, say this engine where we are having bypass ratio to be in the range of 0.25. If I will be increasing this bypass ratio, it will give the benefit in terms of say thrust specific fuel consumption. At the same time, it is also giving benefit in terms of thermal efficiency, but something that need to be observed carefully in terms of accommodating that engine. Say sometimes for special application, my thrust is of major concern compared to my say thrust specific fuel consumption and my efficiency. So, that is where you need to do the compromise in terms of the bypass ratio. Let us look at what is happening with turbine entry temperature. So, here in this case, if we look at by increasing the turbine entry temperature, we will be increasing with the thrust. So, here somewhere we are having say design conditions. Since my thrust is increasing, the specific thrust also will be increasing for the constant mass flow rate configuration, and we know with increase of turbine entry temperature, we will be having say increase on thrust specific fuel consumption, because in order to achieve that temperature you need to inject more amount of fuel, and that is what will be reflecting in terms of efficiency. So, it says with the increase of turbine entry temperature, we will be having reduction in thermal efficiency, increase in thrust specific fuel consumption, but at the same time we are able to achieve higher thrust. So, again here the point is what is our purpose, what we are looking for. Okay. Now, let us discuss in terms of the parameter called say mass flow rate, putting all other parameters to be constant. Here in this case, if we are increasing our mass flow rate, engine mass flow rate, it says that is what will be increasing for say core mass flow rate going inside the engine, that is what will lead to increase the thrust, and the thrust specific fuel consumption if we configure, that is what is remains nearly constant. And if we look at in terms of thermal efficiency, that also is not changing much, but you can understand in order to accommodate this increase of mass flow rate, we need to increase the size of our intake or the engine size. Also will lead to change my nozzle area. The exit area also will be increased with the increase of our total mass flow rate. So, this is giving some other indication. So, when we will be starting with the next week, there we will be using this information. So, just remember what all information we are discussing at this moment, that is what will be having a specific application. Okay. So, this all is representing how my cycle parameters which are affecting the performance parameters. So, now let us move what all we have discussed up till now is in terms of unmixed configuration, single spool, 2 spool, 3 spool. Then we started discussing about the forward fan mixed flow configuration, in which we have discussed without afterburner. Now, let us discuss today with the afterburner incorporation. So, as I discussed, you must have gone through week 4 lecture 18, where we have discussed about the incorporation of afterburner. What is the purpose of afterburner? So, if you recall, it says the afterburners are used for the thrust augmentation. So, let us look at what we mean by thrust augmentation here. So, this configuration what all we have, this is what is similar to a mixed kind of, say, mixed kind of configuration without afterburner, and here after mixing chamber we will be having afterburner. That is what will be next, followed by the nozzle. And this nozzle also, if you look at, these nozzles are of conversion diversion shape. Okay. Now, here let us try to understand what exactly we are doing. So, what happens, the gas which will be coming out from this turbine section or core section, that is what will be mixing with the fan air. Since it is having higher temperature, and what flow which is coming out from this turbine, that will be having, say, some oxygen particles. At the same time, this is coming as my fresh air, that is what is getting compressed. So, we will be having sufficient amount of oxygen, that is what is required for the combustion to happen. Now, the question is, why are we looking for the combustion? Suppose if I want to increase the thrust of particular engine, we know we need to have our exit velocity to be higher. Now, suppose say if I am not having afterburner and if I am looking for my exit velocity to be higher, then I need to go with my turbine entry temperature to be higher. If I will be having my turbine entry temperature higher, I have difficulties in terms of metallurgy, or at the same time I need to go with the new technologies in terms of blade cooling, and that is what is more challenging. Okay. So, in place of that, we will try to increase the temperature at the entry of the nozzle in such a way that we will be having the expansion that will be happening inside the nozzle, which will be giving very high velocity. And here in this case, if we look at, we are not having any rotating component, and that is the reason why my metallurgy constraint in terms of turbine blade, that will not come. Yeah, afterburner, that is also ultimately solid body, there also you need to have some kind of cooling, but the purpose, that is what is served with what all we are implementing with the afterburner. So, again I am advising you to go with, say, lecture 18 and just look at what all we have discussed with. So, let us try to look at the cycle, how it will be modified with. So, very first, as we have discussed, we have our intake, then we have fan or say fans, that will be followed by, say, compressor. We have our combustion chamber here, which will lead to increase the temperature by addition of the heat. It will reach to temperature T05. This combustion process we are assuming that is happening at constant pressure, but we know because of frictional losses my exit pressure will be lower than that of my entry pressure for the combustion chamber. Next we have is in terms of, say, our HP turbine. This HP turbine, that is what will be giving the expansion from pressure P05 to P06. This HP turbine, it is used to rotate the compressor. The gas then will be entering inside the LP turbine, and this LP turbine, which is responsible for the rotation of the fan, or that is supplying the work to the fan. Okay. And that process, expansion process, we are representing from P06 to P07. Now, here in this case, this particular section, that is what we are putting as our, say, mixing chamber. So, in last lecture we have discussed about the mixing process, and it will be happening at some constant pressure. We can say it is at P08, and what is our requirement? It says my pressure from the fan stream and pressure from say turbine stream, total pressure we are discussing about, that need to be same. So, you can say this is representing nearly constant pressure, and this mixing, that is what will lead to reduce the temperature. So, it will be attending some point here, it is 8 point. We can say that temperature as T08. Now, in earlier case what was happening, we were having say expansion, that is what was happening inside the nozzle. So, you can say my expansion will be up to here only. In place of that, what we are doing? We are injecting the fuel in afterburner, and we permit that fuel air mixture to burn in afterburner, and this process we are representing in terms of constant pressure combustion process. So, just look at, if I am adding my heat here, that is what will lead to increase the temperature from T08 to say T09A. That is what is my nozzle entry temperature, and this process we are representing as constant pressure heat addition process. Okay. Now, here this exit, that is what we are representing in terms of 9A to 10A. If I am not operating my afterburner, my expansion will be from 8 to suppose say 9. Here in this case, we are able to increase our expansion work, we are able to increase the exit velocity. Now, the situation is, that is what is called thrust augmentation, that has many applications, mainly for fighter aircrafts in order to do maneuvers, or maybe if they are looking for short takeoff kind of configuration where they will be operating the afterburner, and that is what will be reducing the takeoff time. That is what is very much required. Many times these fighter planes, they need to go with say maneuvers. So, these maneuvers also can be done by using this kind of thrust augmentation or afterburner. So, these are the applications. So, almost all fighter aircraft engines which are being made by say companies called Pratt and Whitney, or maybe say Eurojet, GE, Russian engines, all these engines are of low bypass ratio configuration, and they are with afterburner. So, some of them they are say TF30, say F100, F100 229, 232, 101, F119, Eurojet, GE, they are some of the examples for this kind of configuration. Okay. So, here if you look at, these are the cut section of two different engines. Just look at, here we are having, suppose say let us take this as example, it is F100 Pratt and Whitney, where we are having number of fans here, that is what will be followed by say HP compressor or compressor stages, combustion chamber, HP turbine, LP turbine, and here somewhere you are having say mixing chamber, that will be followed by the afterburner, and this is the exit, and this exit is conversion diversion nozzle, and we have discussed these nozzles are variable area conversion diversion nozzle. So, as per the requirement, you can understand we are adding lot of fuel here, that is the reason why mass flow rate, that is what is coming out from the nozzle will be large, and in order to handle that large mass flow rate, your area requirement also will be large. Okay. So, just look at carefully, say this is most recent engine, we can say 5th generation aircraft, we are saying F135, that is what is working on counter rotating configuration. In next week we will be having the discussion what we mean by counter rotation. So, here also if we look at, we are having say number of fans, that will be followed by HP compressor, that is what will be rotated by HP turbine and LP turbine, and this all configurations are of counter rotating configuration. And here we are having afterburner, that is what has been used for augmentation of the thrust. So, let us look at what we mean by afterburner here. So, this afterburner we can take this as a control volume. So, what is entering inside the afterburner is m.8 H08, and this is the amount of fuel we are adding. In order to avoid the confusion, here we are writing FAB, it is for afterburner, and this will be the exit or say entry condition for the nozzle. So, let us put the energy balance here. So, when we are putting, this is our mass balance, that is at the entry, and if we put our energy balance, it says m dot 8 H08 plus this is m dot FAB, and this will be burner efficiency into the calorific value of the fuel, and that is what is equal to, this is my exit condition from the afterburner. So, let us try to put these numbers. This m dot 8 we know that is what is been written in this formulation. So, if we are putting all together, it says like we will be having our ratio to be coming in this formulation. So, it says my fuel air ratio for the afterburner. Be careful, here we are writing it is m dot f for afterburner divided by what is the amount of air. So, it is a fuel air ratio. That is the reason why dedicatedly it is written in terms of m dot core plus m dot f. Okay. So, do not get confused with the formulation of this. So, if you do your simplification of this equation, we will be having this f term that will be coming in the formula, and this f we know it is very much less than 1. That is the reason why we are taking 1 plus f equal to 1, and if you simplify, that is what will be giving the fuel air ratio for the afterburner. So, based on that we can calculate what will be the fuel air ratio for the afterburner. Now, let us look at what is going in nozzle. So, for nozzle, again as we have discussed, we need to do calculation for the critical pressure ratio. For this critical pressure ratio, we will be checking with whether it is in line with our say atmospheric pressure, is it less than the atmospheric pressure, or say it is greater than the atmospheric pressure. If it is less than, then my exit pressure will be equal to my atmospheric pressure, and we can do our calculation for the static temperature, we can do calculation for the exit velocity. So, this exit velocity, it is written as V10 A. So, do not get confused with the configuration what all we are putting here. Same way we will be having say only single nozzle, that is what is the benefit here. Now, you know like afterburner incorporation is because of we are having the mixing, it is in line to what we can say as a turbojet engine. Okay. So, say afterburner with unmixed kind of configuration, that is what is rare. Maybe if you will do your research and development activity and you will be coming out with some configuration, it will be great contribution to the society, and yes, people they are doing. So, in next week we will be discussing about those aspects also. Here in this case, my critical pressure, suppose it is greater than the atmospheric pressure, exit pressure will be equal to my critical pressure. We can do calculation for the exit velocity. Once we have this exit velocity, we can straightway calculate what will be the thrust. So, for thrust, my exit mass flow rate, be careful, this exit mass flow rate is m dot core plus m dot fan plus m dot f, it is fuel air ratio based, and this is for the afterburner. So, the formulation for the exit mass flow rate, that is what will be modified here. Be careful about this part. Okay. And when we are doing the calculation for the thrust specific fuel consumption, that is what will be not only on the basis of combustion chamber. In afterburner also we are injecting the fuel where lot of fuel it is been consumed, and that is the reason why thrust specific fuel consumption it will be based on m dot f plus m dot fb divided by thrust. We can do our calculation for the propulsive efficiency, that is what will be based on my exit mass flow rate. Same way here in this case, thermal efficiency we need to be careful. This is the amount of fuel we are adding in combustion chamber, and this is the amount of fuel what we are adding in our afterburner. So, do not commit any mistake when you are doing your calculation for with afterburner configuration. And we can do our calculation for the overall efficiency, it is thermopropulsive efficiency, it is a product of propulsive efficiency and thermal efficiency. So, like let's try to solve the previous numerical only with the additional data. We will say our afterburner, that is what is operating at 2000 Kelvin. So, here in this case you can say this temperature it is given to you, it is say 2000 Kelvin, and it says like this afterburner has efficiency of 95% and there will be total pressure loss of 3%. All other information, that is what will remain same. So, let us look at what will be the calculation steps for this. So, we have all our information, that is what is similar to what all we have discussed. Now, we have our afterburner, that is what is been incorporated. For this afterburner, we are given with the temperature, we are given with the efficiency and what is the pressure loss. So, based on that we can calculate what will be the fuel air ratio for the afterburner and what will be the exit pressure from this afterburner, and this will be connected with the nozzle. For nozzle, again we can do our calculation for critical pressure. Based on that we can calculate what will be the static pressure, static temperature and exit velocity, and from there we are able to calculate what will be the performance parameters. So, let us look at what all we know. So, here in this case this information, that is what is already given or known to us from the previous. So, we will not be doing the repetition of this calculation. Okay. So, here in this case this process 8 to 9, that is what is representing constant pressure heat addition process which is happening in the afterburner. Okay. And this process from 9A to 10A, that is what is representing expansion which is happening in our nozzle. Okay. So, this will be a very good numerical. You can say we are solving this numerical for ground condition without afterburner and with afterburner, and we will be checking what will be the effect on the performance parameters. So, all these numericals they are being designed in such a way that you will be having detailed understanding for all the aspects. Okay. So, let us move here. It says in afterburner we have 3% total pressure loss. So, we can have our exit pressure from the afterburner as 370.93 kilopascal. This temperature is also known to us. We can do our calculation for the mass balance. Let us do that part. Say I am putting my control volume. So, just put it here is a say afterburner, and for this afterburner we can write down our energy balance in this way. Okay. So, sometimes as we discussed earlier, people used to say this as a secondary combustion chamber also, primary combustion chamber and secondary combustion chamber. Okay. So, let us put the equation for the energy balance here, and you need to be very careful in terms of mass flow rate what all we are putting. It is m dot infinity plus m dot f plus m dot fan plus afterburner. So, let us put this as a number, and we have done our calculation. Just check with the fuel air ratio for the afterburner. The numbers are known to us. Let us put these numbers. It says my fuel air ratio for the afterburner is coming 0.0332. Okay. So, we have information about the temperature, pressure and the fuel air ratio. Now, this will be the input for our nozzle, and for the nozzle here in this case gamma value we have already calculated for the mixing chamber, that is what is 1.32. This efficiency for the nozzle it is given 95%. So, let us put that number only. Based on that we will be doing our calculation for the critical pressure, and this critical pressure by calculation it is coming 194.2 kilopascal. Let us try to compare this critical pressure with the atmospheric pressure. Here in this case it says my critical pressure, that is what is greater than that of the atmospheric pressure. That is the reason why exit pressure will be equal to critical pressure, and this critical pressure we can say it is 194.2 kilopascal, and we have this nozzle as a choke condition. So, for that condition we can calculate what will be the exit temperature. Be careful, since now we have the incorporation of afterburner, that is the reason my exit temperature will be different from the previous cycle, and this exit temperature it is coming 1724.14 Kelvin. You can understand what number we have calculated, that temperature and this temperature, they are totally different. Okay. Now, based on that we will be calculating our exit velocity, and that is coming 808.19 meter per second. Compared to previous velocity without afterburner, you can see this velocity is coming very high. Okay. Now, similarly we will be doing our calculation for the exit area, and this is given by m dot 10 divided by say velocity into density. This density we can calculate based on static pressure and static temperature. If we put the numbers, it says density is coming 0.39 kg per meter cube, and we have our total mass flow rate, that is also we have calculated based on this equation. Okay. And it says my area is coming 0.2654 meter square. Okay. Now, let us do the calculation for the thrust. Here in this case we have done our calculation for say m dot 10, it is coming 84.16. Velocity we have calculated, our velocity of flight velocity is 0. Let us put this number. It says when we are incorporating the afterburner, you can say previous number and this number, this thrust that has rise to 92.67 kilonewton. Okay. Similarly, our thrust specific fuel consumption, if we are doing this calculation, be careful about the formulation. Here we are putting m dot f plus m dot f a b, and that is giving thrust specific fuel consumption to be 44.9 gram per kilonewton second. We have our propulsive efficiency. Since my V infinity is 0, so propulsive efficiency will be coming to be 0. Let us look at what is happening with the thermal efficiency, and if you look at this number, it says when we are incorporating the afterburner, here in the denominator we are having m dot f plus m dot f b, and that is the reason why we are adding a lot of fuel in afterburner. That is what will lead to reduce the thermal efficiency, and this number is coming 15.43%, and overall efficiency or thermopropulsive efficiency, that is what is coming to be say 0. So, let us try to look at what all we have done with afterburner configuration. It says my area is coming 0.26, the net thrust is 92.67 kilonewton, thrust specific fuel consumption also is increased, and our thermal efficiency is coming to be lower compared to what all we have discussed without afterburner configuration. So, we will try to discuss what is the effect of say afterburner exit temperature. So, you will say if I want to increase the thrust, so for that we need to increase say my enthalpy at the entry of my nozzle, and in order to increase that enthalpy you need to inject more amount of fuel in say our afterburner, and that is how we are increasing our afterburner temperature. So, let us look at what is the effect of this. So, here in this case if you look at say we have our afterburner temperature, that is what is 2000 Kelvin. With the increase of afterburner temperature we are able to increase the thrust. Okay. And you can understand we have discussed my turbine entry temperature, it is nearly 1520 Kelvin, and my afterburner temperature, that is always higher than that of my turbine entry temperature. Okay. If we are moving towards the lower temperature, accordingly my thrust will be reducing. So, it is preferred when you are looking for higher thrust, you need to go with say higher afterburner temperature, and when we are looking in terms of my specific thrust, that also will be increasing. For that constant mass flow configuration, the specific thrust is increasing. Now, when we say our interest in terms of say thrust specific fuel consumption. With the increase of afterburner exit temperature, our thrust specific fuel consumption will be increasing, because we need to add more amount of fuel in afterburner, and that is what will lead to increase the fuel consumption, and that will be reflecting in terms of thrust specific fuel consumption. And as we have discussed, with the increase of afterburner exit temperature, we will be having reduction in thermal efficiency. So, this is what all are the effect of say afterburner temperature. Now, this afterburner, it is being used by fighter pilots as and when required. Suppose say if he or she will be operating this afterburner frequently, he or she need to be very careful in terms of fuel available for that particular aircraft. It may possible that they will be coming out with a situation where they will not be having sufficient amount of fuel. So, the operation of afterburner will be for few seconds. Okay, it is not for the longer duration. Okay. Now, let us see the overall comparison of say your low bypass ratio fighter engine, where we are having our condition as a ground condition. We have done our calculation for the area, exit area. If we look at for say without afterburner case, the area is coming 0.16, and with afterburner the exit area will be increasing. As we have discussed, it need to handle the large mass flow rate because of additional fuel what we are putting in our afterburner. Similarly, if we look at the thrust, it says we will be having the augmentation of the thrust. Be careful here, maybe if I will be increasing my temperature of afterburner, then it may be possible that this number will be moving towards say maybe 100. Okay. Similarly, that all what we are discussing, it will be in terms of fuel economy. So, for fighter engines, we are not bothering of having say fuel economy. I am putting this statement at this moment, maybe in next week I will change my statement. I will say fuel economy, people they are thinking in a different way. Now, for fighter aircrafts also fuel economy consideration, that is what will be coming. That is what we say next generation aircraft, 6th generation aircraft, that will be having some other requirements. Here in this case, if we look at the thermal efficiency for the ground condition, it is 18.67, and when we are having say afterburner, this efficiency will be 15.43%, and this two they are representing the cycle analysis. So, here we are stopping with the discussion for mix configuration, and we are ending this week discussion dedicated for say 3-spool configuration and mixed flow configuration with and without afterburner. I am sure now you are able to understand what all are the application of different types of say turbofan engines. There are many varieties which are available, but where we will be having small changes in the configuration. So, in next week we will be discussing about say recent advances in turbofan engine, where we will be discussing what all people they are thinking, what all designers are thinking, what all engine manufacturing companies are thinking, what all say aircraft manufacturing companies are thinking in terms of having their future engines. So, we will be discussing ongoing research activities for say turbofan engine, because you must have realized for all commercial aircrafts the option is with high bypass ratio engines, and the use of turbojet engine, it is now limited with few applications, but do not forget we have not completely removed the use of turbojet engine also. So, this turbofan engines, what all are the future requirements and what all are the design requirements and how people they are addressing the challenges, this all will be there in the next week. So, have a nice day. Thank you very much.